Okay? So we have our ODE. Next step is to solve this. All right? So let's look at this for a second. How are we going to solve this, this ODE? We have a second derivative. We have temperature appearing now. That's different from what we've had before. And we have a constant. So it's not immediately clear that we could do separation of variables, right? We can't separate this. It's not a separable ODE. Because the minute you try to move dx to the other side, you get it multiplying t. So you can't separate it. So we're going to have to go into a different technique to solve this problem. Okay. First, let's give this a classification. This type of ODE. It is three things. It is a second order ODE. Second order means that there's a second derivative of temperature. Okay, second thing, it is that this is a linear ODE. What does linear mean? It just means that it's not, there's no temperature squared or temperature cubed or whatever like that. There's no, the temperature is only to the first power, even though there's multiple orders of derivative of it. So it's a linear problem, and that becomes really important because it means for a linear problem, we can break it apart, do things independently, and then add the parts back together. Right? And we're going to take advantage of that. The third thing that it is non-homogeneous. Right, so remember back to your quiz that you took that said, okay, is this problem homogeneous or not? If there's stuff on the right-hand side that's only a function of the independent variable, then it's non-homogeneous, which is the case here. We have some constant on the right-hand side, which is technically a function of the independent variable to the 0th power. Right, so it's a non-homogeneous equation. All right, so the way that we're going to solve this is by breaking up the temperature into two parts. So let's see. We're going to make this assumption, and you'll kind of see where this goes. But I'm going to say that T is equal to a homogeneous T and something called a particular T. So again, T is still a function of x. We're assuming TH is a function of x and TP is a function of x. We're going to separate out the parts of the problem, solve them with respect to these two different variables, and then bring them back together, and that'll give us our solution. Okay, so we're going to make this assumption and then make that substitution into the ODE. Right, so this stuff here just gets substituted in for T here and here. Yeah.
So we're able to do this because it's linear.
Because it's linear, yes. Okay, so we make that substitution, and let me just see if I have room. I'm going to move this stuff over a little bit. Okay. So I want to just go through the tedious part of writing this out just so I can show you what we end up with. So we make that substitution and we get the following, which is d squared th dx squared minus perimeter times h bar over k ac times th plus d squared tp dx squared minus perimeter times h bar over k ac times tp is equal to the right-hand side, which is, if you have room, minus perimeter h bar over k ac times t infinity. Okay, t infinity, sorry, that's a little hard to see. Let's try this again. Times h bar times t infinity. Still not great, but you know what I'm saying. All right, so the trick here, or the idea, is again, we have now this part of the ODE that's just in terms of the homogeneous temperature, or TH. And what we're going to do is we're going to say this has to be equal to 0. Okay, and then this becomes the particular part. Okay, so this is a little bit confusing. But what we're doing in this substitution is we're saying, I'm going to find a solution, TP. That solution satisfies this part of the equation. So I just need a function, whatever it is, for TP that satisfies the relationship given here. If I do that, that's great. That's part of the solution. But that's not the entire solution, right? Because I can have an equation that satisfies that particular solution, but it's not the entire possible temperature solution. In order to get the entire part of the solution, we also need to find an equation that satisfies this relationship equals 0. Okay, so think about that for a second. We can take a particular solution, add something to it that equals 0, and we still get the same thing back, right? But it's just a way that we can ensure that we're getting a complete solution for temperature. All right, so let's look at how this actually plays out, unless there's questions on this part so far. Nope. You'll see where it goes. All right, so this is a little hard to see, but the point of this is let's now start with our homogeneous solution. I'll just rewrite it here. So that was d squared th dx squared minus perimeter h bar over k ac times th equals 0. So I need to come up with a solution that satisfies this ODE, right? This homogeneous ODE. So to do that, I can just go to a table like the one shown here, and let's maybe zoom in, and we can find something that looks like our equation. Well, it turns out that the very first thing in the chart looks quite a lot like the equation that we have. So we can use the solution TH equals either the exponentials or quotient sinh, right? They're equivalent. So quotient sinh are formulated in terms of exponentials. So we can pick one of those and use that as our solution. That's our homogeneous solution, right? So let's see. What we also need to do here, though, is note that there's this constant m squared. So all that stuff that's multiplying th that's a constant, we need to translate that into this thing called m squared. So let's do that. Get back here if I can zoom out, maybe. Try this again. All right, so let's use that equation. So we're going to say here, first, m squared is equal to perimeter times h bar over k times ac. What do we know about this? The fact that we're calling it m squared? Always positive. Yeah, exactly. So that means that term's always positive. Always positive. And that makes it easier to solve, or it solves it in a certain way. OK. So subbing that in, let's use the quotient sinh solution. So we end up with th is equal to c1 cosh of m times x plus c2 sinh of m times x. Good, so that was pretty easy. Like that was maybe the easy part. It's just getting that pattern to match and line up. So the next thing we need to do is deal with that particular part of the solution. All right, so let's go back to, this is our ODE that we had for the general ODE up here, and then our particular solution here. So we need to find, like I said, an equation or expression for TP that satisfies this set of operations. That is, give me a function. Let's take the second derivative with respect to x, subtract some constant times that function, and it has to spit out the thing on the right side. All right, so we need to maybe start by guessing something like the right side. In order to get to that, the function probably should look like it to begin with. So the way to do this is, the formal method is called method of undetermined coefficients. Okay, method of undetermined coefficients, sometimes abbreviated MUC. And the idea is, let's look at the right-hand side of the equation when it's in standard form like this, and let's guess a function that is some unknown constant times the function on the right-hand side, and then another unknown constant times the derivative of the function, and then another unknown constant times the second derivative, and so on. Or you just keep taking the derivative of the right-hand side, multiplying it by a constant until you have 0, and then, or until the function repeats. And then you use that entire expression as your guess for what TP is. So this example is pretty simple because we would just say, well, the right-hand side is a constant. So TP, I'm going to guess, is equal to some constant, C, let's call it C3 because we have C1 and 2 from our homogeneous solution. So C3 times the function on the right-hand side plus C4 times the derivative of that function. All right, so we just are going to go through this process. What we end up with is, let's see. Yeah, I'm going to guess that it looks like this. So C3, C4, because the derivative is 0 of those constants. So we're going to guess that TP is equal to C3. All right. Any of like the constants that are coming with that are going to show up in the C3 when we eventually get to it. So we'll just lump everything together, say it's a constant. Now, if this was like sine or cosine on the right-hand side, we'd say this is maybe C3 times sine plus C4 times cosine, right? You need all the different derivatives to appear. But for this problem, it's pretty simple. We're just going to guess this. So, OK, so now we take this back. We're going to substitute this guess in where we see TP and see what happens. So second derivative of C3 is going to be 0. So this becomes 0 minus perimeter times h bar over k AC times C3 is equal to minus perimeter h bar over k AC times T infinity. OK, so what did we learn? I guess we learned that C3 is equal to T infinity. Furthermore, because C3 is T infinity, TP is T infinity. All right? That makes sense to everybody? So now what we have left to do is to add the two pieces back together, because originally we said T is TH plus TP. So now my full solution is going to be T is equal to the part we had before, which was the C1 cosh of m times x plus C2 sinh of m times x plus TP, which is T infinity. OK? So hopefully now you see this process and why we have to do both parts. Because if we had just found a function that satisfied the particular equation, we would have just said T is T infinity. Right? And that's not the complete solution. The complete solution is where both of the conditions are met, where you have the part that equals 0 when we're doing the derivative operations, and then the part that's a constant, or the part that is the particular solution. Right, so this is now our general solution. What you should also notice is there remain in this two unknown constants. Right, if you go through the method of undetermined coefficients and you end up with like 6 unknown constants, you have a problem because you only have 2 boundary conditions. So you better come out of that entire process with the right number of constants.